Hey everyone. Thank you for the invitation and the talk. I'm an applied ML engineer at the Vector Institute, where I mostly work on LLM infrastructure and training. And currently, I'm focusing a lot on essentially building out like the infrastructure for a lot of our faculty members, especially for optimized large language model training. So today I'll mostly be talking about just a few basics of transformers. Presumably not many of you would like need that like primer, but I'll just go over it just to make sure everyone's on kind of like the same page. And then I'll kind of shift the focus of the talk towards more so about distributed training, kind of what distributed training is, and what goes into it, how we can optimize it, what are some of the issues that can arise once you like scale beyond a single GPU. So essentially there are 25 slides and there are 25 minutes for me to talk. If there are any questions that like arise in the middle, just like feel free to just interrupt me whenever. But I think there should be like some time for Q&A at the end as well. Cool, and everyone can hear me okay? I'm not really using the mic here. Okay. So just before I start, I just want to give some due credits because a lot of the content over here is not really mine. I've just like kind of collated everything into one presentation just for ease of access. So a lot of the introduction stuff is from Jimmy Ba at U of T, and a lot of the illustrations for transformers and distributed training are from JLMR code here. So here's a quick overview of the talk. So I'm going to start by talking about like decoder-only transformers, which a lot of people are kind of interested in because those are the large language models these days coming out of like these big companies. And then I'm going to switch, as I mentioned earlier, I'm going to be switching over to more so talking about how we can scale beyond a single GPU for larger model trainings with FSDP. And then we'll talk a bit about like throughput optimizations, and I'll have like one final slide on like takeaways that you can make use of starting today. Cool. So this is a quick like diagram of GPT-3. Essentially just showing how kind of inference works within these large language models. You essentially feed in some sequence. In this case, it's like the robot must obey the orders given it. And then the transformer model essentially autoaggressively generates a new token one by one. And for the purposes of this talk, I'm just going to refer to token as a word, but in reality, as probably most of you know, a token is a subword in most cases. Yeah. So I'll quickly touch over like two of the most like important building blocks for these decoder-only transformers. Namely, they are like self-attention and the MLP layer. There are a lot of other things that go into these transformers, such as like, the tokenization, embeddings, normalizations, positional encodings, and all that. But like for the sake of time, I'll probably be skipping over most of that stuff and just focusing on these like two main like computational blocks within the transformers. But for the sake of anyone reviewing the slides at a later point, all of this is like included in the slides. It's just that I'm skipping over them for the talk. So going over like self-attention and how it works. So there are three kind of key ideas behind self-attention. Firstly, we'll talk about like the query. So the query is essentially a representation of the current word in the sequence. And essentially this query, in this case, if you see here, this is the word it with the associated representation. And this is used to score against all of the other words in the sequence using their respective keys. So you can think of this as a bit of like a dictionary lookup for those of you like who have some idea of how like Python data structures work, or even like a hash map. So there's like keys and values associated with this kind of like whole list of key value pairs, and then you have a query vector that you're matching against them. So yeah, so coming to the key vectors, these are essentially like labels for the words in the sequence. And they're what we match against, what we match the given query against in our search for relevant words. And finally, the value vectors are the associated like actual word representations. And once we've scored how relevant each word is, these are the values we add up to represent to end up with like a final representation of the current word. So how do we get these QKD vectors? Essentially, each attention block has three matrices: WQ, WK, and WB. And these are what create these vectors. So essentially, if you look down here, X1 is the representation of the current word. So X1, X2, X3, X4 are all like individual tokens. But let's just focus on X1 for now. Essentially, it will multiply to each of these three matrices, and you end up with K1, K1, and B1, which are these three vectors that I spoke about on the last slide. And this happens for every single incoming token. And then to calculate the kind of the similarity or the matching phase, essentially you do a cosine similarity or like a dot product between the query vector and all of the key vectors. So that's what you see over here. And this gives us a score. And essentially to ensure that it all adds up to one, we apply the softmax operation, which is giving like a probability distribution over like the multiplier. So essentially you take a dot product across all of these representations, apply softmax, and then you end up with these scores up here. And so essentially with these scores at the end, we multiply the value vectors. So that's the reweighing stage almost of how similar each value vector is with a given query vector. And then you add them all up and you end up with that representation up there. So Z1 in this case. And this essentially happens for all of the incoming tokens. But in this case, I'm just referring to X1. However, for decoder, like what's special to decoder-only transformers is that it's masked self-attention. So what's different is that essentially for a given word or a given token, all of the future tokens on the right-hand side will be essentially masked out. So the given token essentially is not allowed to look into the future. So before we apply the softmax operation, we essentially mask out the future values and then softmax it to essentially adjust the probability distribution over the current word and the ones that came before it. Yeah. So that's essentially how self-attention works for these decoder-only transformers. There's not much more to it. And then right after the self-attention layer, we have the MLP layer. And this essentially takes the outgoing representations and just we go through like a two-layer MLP. One is what's called like like it upscales it. So the incoming representation size is 768. And then we do this upscaling over here. So on GPT-3, what's specific to GPT-3 and GPT-2, they just add like a multiplier of times 4. So we upscale the inner subspace to like the 4x the size of the representation coming out of the attention block. And then we down project it back down to the original one, which is 768. And that's essentially the MLP layer. There's not like a lot more to it. And yeah, so that's essentially like the two main parts of what goes into the decoder block of a decoder-only transformer. Of course, like I've skipped over like a bunch of like the nuances, like the normalizations, the skip connections, and all that. But these are essentially where most of the computation ends up happening within the decoder block. And as far as scaling up these large language models go, you essentially just stack a whole bunch of these decoder-only layers a bunch of times, and that's how you end up with like these super large models. That's just the gist of it. Of course, there's like some details here and there, but that covers a lot of ground for us. So I'm gonna switch over to a few challenges we have with scaling. I'm gonna pause for like 3 seconds if there are any questions up until this point. Okay, cool. So yeah, as we saw earlier, essentially creating these large models is only a matter of stacking these decoder blocks a whole bunch of times. So everything's great while things fit into a single GPU. So things like your model parameters, your parameter gradients, your optimizer states, and like forward pass activations. However, as soon as we start getting to these larger models where all of these things start to scale up, we hit barriers that require us to go beyond a single GPU. And so one way of circumventing this problem is by using what's called fully sharded data parallel, or FSDP for short. And before I get into what FSDP is, I'm going to take like a quick kind of like detour into like the world of like distributed computing, and just clarify a bit on like the jargon that I might end up using while I'm explaining how FSDP works. So first I'll go over what's called the all reduce operations. So in this diagram over here, rank 0, 1, 2, and 3 are essentially 4 GPUs. And essentially what the all reduce operation does is, so assume that each rank or GPU over here holds like an n by m matrix. And once you run the all reduce operation, in this case, it's the sum operation. So what happens is that you take the sum of all 4 matrices over here, and then each rank will hold the sum of all of them. So you just sum all of them together, and essentially each rank will hold that same exact summed up matrix. And that's essentially what the all reduce operation is. And it doesn't have to be a sum. It can be any sort of like reduction, like averaging, summation, etc. But yeah, so that's essentially what the all reduce is doing in this case. The next one is called an all gather. So in this case, assume that each rank holds an n over, like divided by the number of GPUs, so like n over 4 by m matrix. And so it has these like kind of like sub blocks for each rank. And when you run the all gather, it's the concatenation of all of these sub matrices. So now once you run the all gather, each rank will hold the same concatenation of all these like 4 sub matrices, I guess. So this is like an n by n matrix, n by n matrix, n by n matrix, etc. And finally, the last one is called the reduce scatter. It's similar to the idea of the all reduce that I spoke about earlier. Again, assume each rank holds an n by m matrix. When we run this reduce scatter operation, we perform the reduction operation as you would have done earlier. So in this case, once we run the all reduce, we will have that same like n by m matrix at the end once you run the all reduce. But the scatter operation essentially scatters the like the final reduced matrix to the respective ranks. So you can kind of think of it as like running an all reduce and the inverse of like the all gather. So you're going like backwards. So you have the reduced matrix, but you scatter the reduced matrix to the respective ranks again. And yeah, so that's essentially the 3 operations that are key to understanding how FSDP works. So here I'll quickly go over what FSDP is doing. So if you look at this GIF over here, sorry, this is like irrelevant, but yeah, okay. So now you'll see like as you scale up the model size, all of these things scale up. And what FSDP does, it essentially shards or splits up all of these states and puts them equally on the available GPU. So in this case, there's 3 GPUs. And so your optimizer, your model, and your gradients will be split into 3. And they will reside in this chunk format across the 3 GPUs in this case. So the algorithm is actually very simple for FSDP. So during a forward pass for a given layer in the transformer, what happens is that, so as I mentioned, you know, how all of these split up against along the 3 GPUs, you first all gather the layer weights. So you will, you know, concatenate all the layer weights of the given layer on each of the GPUs. So now each GPU holds the weight of the given layer. You compute the forward pass since you have the weight matrices for the given layer. And then you essentially you get the activations out, you keep the activations, but then you discard the weights except for what the GPU is assigned. So at the end, you still hold on to that chunk of yours, but you will discard like whatever was not assigned to that GPU, but you will still have that full activation for that layer. So that's essentially the forward pass. That's the entire algorithm of how the forward pass works. And for the backward pass, it's actually like very similar. So if you recall how backprop works, you need the weight matrices and you need the activation to calculate the gradients going backwards. And also, well, the last layer's gradients. But essentially, you will all gather the layer weights for a given layer during backprop. And then you already have, so from this step over here, you already have that full activation kept on the GPU. That's not discarded. So what you need is the layer weight. So you all gather the layer weights first. You compute your parameter gradients using the weights and the layer activations going backwards. And then again, similar to step 3 over there, you will discard the weights that you no longer need, except for what the GPU is assigned to hold. And then finally, because each GPU will have its own batch of data, the gradients for each GPU will also be different. But to ensure that like the model updates across all GPUs are the same, you need to average the GPU. You need to average the gradients across all the GPUs. So this is where you run the reduce scatter operation. So you will do a reduction of all the gradients across the GPUs, and then you will scatter those gradients. So then whatever chunk each GPU holds, will get those gradients and it will perform the weight update. And that's essentially how FSDP works. Yeah. And this allows us to essentially scale to larger models. Companies like Microsoft have scaled this to like almost, I think it was 500 billion parameter models. But as far as what we've tested at Vector, we've tried this up to like 13 billion. And it scales great. And this is the entire kind of algorithm of how it works. So that was a lot of talking. Are there any questions or clarifications anyone needs for the kind of the FSDP algorithm? Yeah.
So what's your bottlenecks? I mean, you sort of have to equally spread them out when you want to sort of get an effect. Where's the bottlenecks in the connects?
Exactly. Yeah. So I was going to get to that like in the next slide or so. So you can imagine that like once your these states are beyond one GPU and you need to be rematerializing them on the same GPU, you need to be communicating them constantly over some sort of connectivity between GPUs. And that's essentially where most of the bottleneck comes in. And I'm actually going to go through like almost like a bit of like a case study that we had at Vector, like one by one, and how we kind of optimized this throughput and circumvented the problem of slow like interconnect between GPUs. Because like especially at Vector, the problem is like we have really strong GPUs, like we have like A100s and A40s, but the problem is like I think, at the time when we were buying them, I guess we didn't like foresee this, but the connectivity between the GPUs is poor. So that's where the major bottleneck kind of comes in. So I'll spend like most of the remainder of this talk kind of going over those problems.
New ones though.
Pardon me?
Not those new chips, they talk to each other.
Which ones are you referring to exactly?
The H100s.
I'm not too familiar with like the workings of like the H200 or the H100. Oh, okay.
I saw them.
Okay.
Jensen came out and was like,
Sorry, was there a question? Okay. Cool. So, yeah, so I guess he set it up, perfectly what I was going to get into. So the following, like I'm going to go over like kind of the case study over here. So these experiments were conducted on A100 GPUs. So these were top of the line GPUs. And that each have 80 gigabytes of VRAM. And so each node, or in other words, machine, has 4 GPUs attached to it. And so some of the experiments will be conducted on one node and some of them will be conducted on 2 nodes. And so this is the super important part. So the connectivity within the node, so amongst the 4 GPUs, is 300 gigabytes per second, but the connectivity between nodes, so between machines, is only like 6 gigabytes per second. So like just these two statistics are a little important to keep in mind. So this was our very first kind of training attempt at vector, and I'm just gonna quickly go over like the setting and the outcome. So we were just doing like continued pre-training, just like regular like next token prediction. We had a data set of about 1 billion tokens, a text data set, and we were training Llama 7 billion model. And so the hardware we were working with was 2 nodes of A100, so a total of 8 GPUs. And so the outcome was super poor performance. You know, we had our training throughput. So throughput in this case is referring to the number of tokens we compute for the forward and backward pass in a given second. So we were only going over like 1,400 tokens per second over 100 GPUs. So this is super slow. Just to process a billion token text data set, it took us over 8 days for that one epoch.
Sorry, quick question.
Yeah.
That insane GPU, why not use 7 billion?
So actually it turns out that like you need to like for a 70 billion model, you actually need like more GPUs just because the atom optimizer states end up taking like a lot more memory. So you actually need more than 8 A100s for like a 70 billion model. But turns out like you can actually fit a 7 billion model on like a single node. This was essentially like our first attempt of trying to optimize like fine-tuning of these models on our cluster.
And this is the raw model without quantization.
Yeah, this is full rank like FP16 fine-tuning. Cool. Yeah, so going back to the communication bottleneck. So over here, we're doing FSDP essentially over the slow intranode communication, which is only like 6 gigabytes per second. And the bottleneck comes because there's a communication overhead for the FSDP communication of weight gathering and reduced gathering over that slow interconnect. And so essentially the lesson here was like, you know, more GPUs is not always better if your communication can't support it. And you need to, like, while you're scaling up, and you end up caring a lot more about not just what accelerator you're using, but also like connectivity, the hard disk, and all these things start to like play a big role. And so essentially we, like a very like, you know, hacky solution was instead of using 2 nodes, why don't you just use a single node, which has a super fast intraconnect? And so just doing that, going from 8 A100s to 4 A100s, so having the number of GPUs, we essentially removed this internode communication dependency, and the training throughput increased by almost like 6-7x, and we were at 8,000 tokens per second for training. And total training time went from about like over 8 days to just under a day and a half. So yeah, essentially like communication plays a big role, and this is kind of like showing that like, you know, you need to keep in mind how your communication plays a role into your whole training pipeline. So we also incorporated flash attention too. It's essentially like an input-output aware attention algorithm that minimizes the number of reads and writes between the GPU's high bandwidth memory and the on-chip SRAM. So over here, this kind of like the hierarchy of how RAM works in the system. So at the bottom, you have like super slow but very large CPU DRAM. Then you have the GPU's onboard VRAM, and then you have the GPU's SRAM. And so the SRAM is the smallest, but it's the fastest. And so this is the entire hierarchy. So essentially what flash attention does, the computation for your attention multiplications, like the matrix multiplications, they're essentially tiled. And so each tile is computed on the SRAM, which is super fast. So this essentially increases speed and reduces memory usage. from quadratic to linear in terms of sequence length. And so once we essentially employed this, we saw a significant performance gain once again. So as previously, without flash attention, we had like 8,000 tokens per second. But with using flash attention, we doubled that throughput. So we were at 16,000 tokens per second at this point. And so training time is now from just over 8 days to under a day now. And so now what's the problem? So now we have idle compute. We're doing all this on a single node, but in reality, we have another node that we can make use of. So what do we do? Essentially, there's this thing called hybrid FSDP. So if you recall, FSDP does all this communication for like weight gathering and reduced scattering for a given model. So what's the solution we can have? So essentially within one node, we can have FSDP. So we have two nodes. We can have FSDP in both nodes happening. So all that communication is happening over super fast connectivity of 300 gigabytes per second. But we essentially average the weights on the slower interconnect, which is 6 Gbps. But essentially, we reduce the number of the volume of communications happening over the slow interconnect by doing this hybrid kind of solution. So yeah, implement FSDP within one node and implement data parallelism across nodes. And what this does is now we can actually use this second node that we have on hand. So when we were not using a hybrid shard across 8 nodes, we were with flash attention and everything, we were at 6,500 tokens per second. But with the 2 nodes, we're up from 16,000 to 24,000 tokens per second as a throughput. And now training time is just under 12 hours from 8 days. And yeah, final bits of optimization. So NVIDIA GPUs have these things called tensor cores. And essentially, I'm running a bit over time, but just very quickly, we have these tensor cores that can be activated essentially when your tensors are of shapes of 2. And on certain data types, so FP16 and whatnot. And then the other thing is we can use what's called activation checkpointing. So over here, you can think of each node as a layer. And so you essentially, so this in this GIF over here, this node is checkpointed. So what the benefit of this is, instead of storing all of the activations, you only store some subset of the activations in the whole computation graph. And during the backward pass, if you need, for example, like this layer's activations, you only need to do a forward pass from this node over here. You don't need to do a whole forward pass. So it's a balance off between like performance and memory. And this essentially allowed us to like scale up our batch size and whatnot. And just some consequent optimizations, just a final slide. So flash attention is a linear relationship between sequence length. So since we had some leftover GPU VRAM, we essentially extended the training context length in our experiments from 2048 to 4096 tokens. And essentially this allowed us to saturate our GPUs. And so what this did was it essentially allowed us to go from 24,000 tokens to finally a 30,000 token per second throughput. And this is a 20x throughput improvement on the same exact hardware. And so we've gone from, at the beginning, we were at 1,500 tokens per second, but we've ultimately ended up at 30,000 tokens per second. And yeah, so training time ended up going from like 8 days to, I think it was just 16 hours when I last checked. And yeah, these are just final takeaways for today. So I'm assuming a lot of people here, even if you are doing fine tuning, you're only restricted to a single GPU for the purposes of like the bootcamp, or sorry, the hackathon. And so essentially for single GPU workloads, the single most important thing you can do is use flash attention and mixed precision training. And both of these things are kind of available, like they're built into most like based pipelines and models. So it should just be a matter of like flipping a Boolean flag to make use of these. And for those of you who are fine-tuning LLMs outside of this hackathon, we've also open sourced a library from Vector that has all of these optimizations built in. It's called Vector LM, and you can just look it up on GitHub. There's also a link over here if you want to make use of it. And yeah, that's all. Thank you.
Thanks so much. Any questions? I think we went through the questions during the talk. Thanks
Yeah,
a lot.
yeah. That's good.
Next we go with Marta because swap that position with Rod. Mara, can you help with the slides? Great. Next person is Marta from LLM Physics Lab. She's going to tell us about language models in the lab. Thanks so much.
Cool, yeah, thanks for the intro. Hi, everybody. My name is Marta. I am a PhD student in Alon Asper Physics Lab. And today I'm going to tell you about how we are using language models in the lab to drive experiments and, well, we hope one day material discovery. We're not quite there yet, but that's the goal. So this all started with Alon coming out with a perspective piece in 2018 about what the ideal scenario would be in a lab, the interaction between a human and a robot assistant. So he created this character called Organa. And the chemist here, Jane, has some experiments that she needs to run. So she talks to Organa, she tells Organa what needs to be done. And then Organa's like, yeah, no problem. Come back in 3 hours. Sounds like a dream to me. And then Jane comes back in 3 hours and everything's done. So this is sort of the inspiration that we've been building off. So I'm going to tell you sort of how far along we've come towards this vision. So self-driving labs can mean a lot of things. Even in our lab, we have 2 types. So this is one of our robots, which is a ChemSpeed. So this is what we use to do really interesting chemical reactions. And there was a paper that came out. So now it was accepted to science, but it was on the archive since 2023. But it was a collaboration between 5 different labs across the world. And it showcased how this collaboration could be used to generate or find a new organic laser that's state of the art. So this is a really cool example of how we can all work together and then come up with state of the art material. So the ChemSpeed is really great. It can do very impressive chemistry, but there are also cons to it. So some of them are that if something goes wrong with the ChemSpeed, it can be hard to fix. You have to fix it yourself. You have to figure out how it works. It can also break down more often than probably chemists want it to. So that could also get a bit tedious. And also the space that the ChemSpeed can operate with is constrained. So you have to predefine the sets of chemical reactions that it can work with. And if you introduce anything novel into the system, then it can be hard to adapt to that. So because of that, we've been working towards a second kind of robot perspective, and that's using a generalist robot arm. So the motivation with this is that you have just an arm and it can sort of act as a chemical assistant. So it could do anything that you want it to, and it can sort of adapt to any changing circumstances. But the issue is that our robot arm can make a lot of mistakes. So it's not quite perfect. We have a long way to go. Yeah, we love it, but yeah, it can make mistakes sometimes. So the first thing I'm going to tell you about is a work that we did to go from telling the robot arm what to do using natural language. And then, I mean, it can still do those mistakes, but we're trying to reduce the amount of times that it would do something like that. So over the last 2 years, there have been really impressive results showing how large language models can write code. And so we wanted to see if we could apply this to our chemistry robot. The issue is, though, that when large language models generate code, they're usually not executable out of the box, and they can make a lot of mistakes. So for example, here I asked, at the time it was GPT 3.5, to create a robot plan for this very simple chemistry procedure, and it created something that looked like Python, which is good, but the problem is that our robot arm doesn't understand Python, so it wouldn't be able to interpret that. So our robot operates using a language called KDL, which is a domain-specific language that, based on our experiments, we assumed that GPT didn't have a lot of access to. And so it didn't really know what it was. So even if I asked it, can you convert it to KDL, it would not really, it wouldn't create something correct. So the first thing that we realized was that if we tell it the rules of this domain-specific language, if we sort of guide it through all of the actions that it can take and the grammar of the language, it can start to generate something that looks more reasonable and looks closer to what KDL actually looks like. So that was really great. We were really excited about that. But there were still some issues. And the issues were that even if it generated this structured language, it could still make mistakes. And while these mistakes may seem small, like it can get like the attribute names wrong, or it might get some spelling incorrect, or it might choose the wrong hardware vessel that you have in your environment, this is catastrophic for the robot because it would be able to execute that. So motivated by that, we knew how to pick out what whether or not there was a mistake. So based on that insight, we create a model called Clarify, where we would take a natural language description of a procedure that a chemist wanted to do. We would run it through the LLM with a description of the target domain-specific language that we wanted to output in. And then we would get something that was unverified structured language. So it was getting there, but we couldn't verify that it was correct. We then passed it through a verifier. So this is a checker to make sure that everything in the language is permissible. And if it wasn't, we would pass that back as feedback to the language model. We would say, hey, these are the mistakes that you've made. Can you fix these now? And then we would sort of go through that loop of generating unverified structured language and then verifying it until we would pass the verifier. Once it passes the verifier check, we could then confirm that at least the plan was syntactically correct and the robot wouldn't fail because of something wrong in the language. So we tried out our model and compared it to a baseline that was that is used for generating KDL from natural language. And we found that our model was able to not only more often synthesize plans and not be like, I am shutting down and cannot generate a plan, but it was also preferred by human chemists. So we had a bunch of chemists label random descriptions, and they found that the plans generated by Clarify were able to more holistically capture the input natural language experiment description. So we were pretty excited about that. We then built a web interface that people can use. You do have to provide your own API key because we do not fund that, but in principle, you can use that. And then we also showed it on a bunch of experiments that we can do with our robot. So we do not do chemistry as interesting as we can do on the chem suite by any means, because we're in a computer science lab. So we could only do very simple kitchen chemistry experiments. So the first was a titration that we did with red cabbage and baking soda. So I guess, yeah, here you can see the natural language description, and then Clarify would process it, and then you would get the robot code out. We also used it to create a margarita. So a little, bartending chemistry there. And then we also used it to demonstrate that we can recrystallize things and then also determine if determine the solubility of a solute in a solvent. Okay, so that was step one in showing one simple step of the chemistry experiment. We then wanted to go back to the organa that Alon proposed in his 2018 paper and see if we could build that into a more complex multi-step system. So with that, we brought organa to life. So we created a pipeline where Clarify is a single module, in that for a single step, we're able to generate robot code, but we wanted to connect it to a higher level reasoning of being able to plan a whole chemistry experiment that requires multiple steps. So Organa works by first interacting with a chemist. So Organa will first talk to a chemist and figure out several key things that it needs to run an experiment. So these points are the goal of the experiment, what equipment and reagents Organa has access to, an example of how to run one step in the experiment, the reasoning behind that step, and the expected results, and also the stopping criterion. So the startup phase requires a lot of information gathering because it needs to know the context of what it's doing. But if the experiment is like 17 steps, then in the end, this is saves quite a bit of time. Is there a sound? Oh, awesome, thank you. So this is a video demonstration of Organa in action.
Hi, my name is Organa. I am a robot chemist.
That's
Can I
not
help you
Organa,
with
that's
anything
me.
today?
Organa.
Hi, Organa.
Behind the scenes.
I would like to run a chemistry experiment.
Could you please specify what the experiment is?
I would like to generate a Torbay plot for an unknown quinone solution.
What is the setup of the lab environment? What are all the reagents and vessels?
So in my lab environment, I have a 10 millimolar solution of an unknown quinone. I have water, I have a 1 molar solution of sodium chloride, and I have 0.5 molar solutions of pH buffers ranging from pH 4 to pH 9. I also have 2 beakers, 1 experiment beaker and 1 waste beaker, a potentiostat, and a pH probe.
What is the rationale behind the experiment?
So the goal of the experiment is to measure the potential of the quinone solution at various pHs. We'll start at pH 4 and take a measurement there, and then we'll scan from pH 4 to pH 9.
Could you please provide an example of how to run this experiment?
Yep. So to run this experiment, I would first add 6 milliliters of pH 4 buffer solution. Then I would add 3 milliliters of sodium chloride solution, followed by 15 milliliters of water. Finally, I will add 6 milliliters of quinone solution. Then I would measure the pH and run a TB scan. And finally, I would transfer the contents from the beaker to the waste beaker.
Can you tell me what the expected outcome of the experiment is?
So I expect that the pH of the solution of the first experiment will be around 4, but a little difference is okay. Now, because it's the first experiment, I don't know what the potential will be, but the general trend is that as the pH goes up, the potential becomes more negative.
What is the number of experiments to be run in total?
6.
What will this be used for?
That is the washing beaker.
What will this be used for?
That is the scale.
Okay, thank you. I will start the experiment and let you know if I have any questions. The experiment has been completed. Here are the results and the report summary.
Thanks.
Yeah, so that was a quick demonstration of how Organa works. One thing I forgot to mention was that
The questions that were asked from you, were they hard coded or it was generated by the robot?
yeah, so the way that it works is that Organa knows the goals of the questions it needs to answer. So it knows it needs to acquire 6 pieces of information related to reagents and examples and stopping criteria, but the order is not hard coded. It'll ask a question, listen to the answer, and then sometimes it'll re-ask the question if it feels like it doesn't have enough information. So that part isn't hard coded. It can sort of, it just knows it has to satisfy 6 answers. Yeah.
So does it have the ability to sort of optimize the process? Let's say we have a couple of compounds that can synthesize in parallel. Does it understand how to do that in parallel, or if they have multi-armed robot, do they have the ability to, sort of optimize the process to, finish the process as fast as possible?
Yeah, it's a great question. So one of the things in the video was some of the actions were happening in parallel. So we did implement sort of a parallelization of actions that it could do given the constraints of the system. So when the robot arm was polishing the electrode, then the pump was free. So it was able to pump out a solution while that was happening. So that part was not done by me. So I can't comment too much on how generalizable it is, but in principle, yes. If there are multiple robot arms or multiple things that can be done in parallel, then our system can sort of figure out how to do that.
Does it understand the chemistry behind that? Let's say how the chemistry process works behind, or we should do that in advance, or we should like in the common prompt, we should show that these can be done in parallel.
So based on the experiments that we've tried, that is figured out during the initial starting phase. So based on, so for example, there is prior knowledge about what a Poiret plot is, which is the goal of the experiment that we were doing. And it is able to extrapolate pretty well based on the examples that you give it and the goal based on what experiments should be. And everything sort of was reasonable in that it would propose pHs that were like super acidic or super basic. It sort of like started at the starting point that you gave Organa and then worked around it to sort of work towards the goal. So based on our experience with the experiments that we tried, it was pretty reasonable. Yeah, so I guess the video seemed to sort of do things pretty smoothly, but this is sort of what's going on behind the scenes. It's a lot more complicated. So we have several different modules. The one that you saw started off with sort of the LLM based interaction and reasoning, where that was the interaction between the human and Organa. And then behind the scenes, it goes into building robot code with Clarify and doing task and motion planning. Oh, thanks. And there's also a perception module that is able to scan the scene. So at the beginning, Organa was asking what vessels are used for. So that a camera will automatically scan what vessels are in the environment, and then the chemist provides semantic meaning. So if you have multiple beakers in an environment, you don't want to mess those up, and you want to know what each one is used for. So Organa clarifies that at the beginning. And then also we have an analyzer module that takes in the results from an experiment and then sort of pings the human if anything is kind of weird or unexpected, and can also do data processing. So the goal by the end is that the chemist is provided with a report summary of everything that happened and also any sort of plots. So here's an example of the output that we got from doing the electrochemistry experiment. So the main, the first question is about timing. So here in the red bar is the time that it takes for a human to perform the chemistry experiment. And here's when we have Organa perform the experiment. So you can interact with Organa either through speech if you like talking, or typing if you don't. And so while the overall time is longer, that's because our robot is a little bit slow. So the actual time that a human spent doing the experiment is in the colored bars. So it's a lot less than what a human would be doing if they were just doing the experiment manually. And then we found that the overall results from the experiment were pretty comparable between Organa and the human. So yeah, we obtained the same results that we have. So an open question, a big question is sort of how comfortable humans are with robots in the lab and how they want to interact with robots in the lab. So we did a user study where we got chemists to perform the experiment manually. not the full experiment because we would have been there for several days, but a portion of it, and then repeat the experiment by interacting with Organa and then having Organa do the experiment. And we found some really interesting insights from this user study. So the first good thing was that users were a lot less frustrated interacting with Organa than doing the experiment manually, which is good because it's a very tedious experiment. They also felt that the physical burden was less. So this is also good because we can motivate this for using this kind of system for people with physical disabilities. And the thing that we found interesting was that humans like to be kept in the loop during the experiment. So they didn't want to sort of like tell Organa at the beginning once what they wanted, and then just, okay, like, see you later, I'll come back in 3 hours. They wanted to be pinged when something was weird or to confirm things, which is interesting because that sort of suggests that we should think about how to keep humans in the loop, but also not to sort of ping them every 5 seconds and have them babysit the robot, because that would defeat the purpose. Yeah, so these are just sort of more low-level details about what's actually going on behind the scenes in Organa. So we use a bunch of different text-to-speech, speech-to-text modules. We use OpenAI Whisper, which is really good, GPT-4, which is pretty decent at planning the full experiment. And yeah. Okay, so the last thing I'll briefly talk about, this is less chemistry related, but we can think about it in the context of using robots in the lab. So we created we worked on a project called Replan a little while ago. And the point of Replan is that things go wrong all the time. With robots and humans, things never go as expected. So we want to have the ability for a robot to be able to figure out if something is going wrong and then adapt to those as it's executing the experiment. So one issue is that if you sort of give the robot an experiment at the beginning, chances are that it should be able to adapt to things that change. The conditions in the environment won't stay exactly the same for the duration of the experiment. So to that end, we created a model called Replan, where we sort of have the robot, or we have the LLM sort of given a goal, identify the high-level plan of what it needs to do to accomplish that goal. Then it breaks down that plan into subtasks. It will go and do each subtask, and then it'll figure out whether or not it did that subtask correctly. So for example, if it has to place something in a bowl, it needs to check whether or not that thing is actually in the bowl. If it's not, then it needs to replan and readjust and figure out how it can sort of fix that. And yeah, so we sort of created this workflow of having a high-level planner that is responsible for making sure that the overall idea of the plan is being executed. Then we have a module for subtask controls, where we give the robot access to sensors like a VLM, a vision language model, but you can imagine having other sensors like temperature or pH sensors, and then making sure that the condition for that sensor is met, and if it's not, replan until it is met. So here's a motivating example. This is super not chemistry related. It's a very toy example, but the idea is here that a robot needs to open a cabinet, but it can't because there is a red block in the handlebars. So it's trying, it's like, I can't open the cabinet. So it calls on a vision sensor, and then the vision sensor is like, oh, hey, there's like a red block in the handle, so you should probably remove it. It removes it, and then it can accomplish the goal of placing a yellow cube in the cabinet. So these projects involve a lot of different people. Not all of them are listed here, but these are the main ones. These are my wonderful collaborators across 3 different labs at U of T and now Georgia Tech. Yeah, and that's all I have to present you. These are QR codes if you're interested in any of the projects that I mentioned, and happy to take any questions.
Any question?
Of failure or maybe lack of resources. If the end product is not viable, according to the current configuration, does one have any idea that what would be plan B, or how we can optimize the process to produce something that is similar to the end product that we are expecting?
Yeah, it's a good question. So currently in the replan framework, we're only doing it in simulation. And so if it tries to replan and it still fails to achieve the goal, it has the ability to explore through the high-level planner. So there's like an exploration policy, I guess, that it will try new things. All of our tasks were in principle solvable. So if it is unable to sort of solve it within a certain amount of time, then we say it's not solvable. But in terms of like similarity of, okay, you're not able to solve it this way, but you have like you need a lemon, but you don't have a lemon, you have a lime. Can you use that instead? That we haven't really tested. So it probably wouldn't be able to work in that setting. I think there is some robotics work that did show that. I forget the name though. But yeah, it is an interesting question of like when you're allowed to replace something versus when you're not allowed. Because in chemistry, that's really important. And you need a lot more background knowledge to be able to figure that out.
Any other question?
So could you comment on the efforts put into getting the robots or your automation equipment to speak IDL, and essentially drivers, and having that interface? Because clarify and organic, like we're mainly interacting with as with IDL as a layer, the robot, not directly with any of the robotics.
Yeah, so if you look at the what you don't see is the bags under all of our eyes in terms of the time that it takes to integrate all these things. But yeah, it is a big effort so KDL is hardware agnostic in that in principle, you can use it on any tools that you have in the lab, but it's up to you to code that interface between KDL and how it interacts with every object. So that is labor intensive. Yeah.
How comment at all on the specific setup that you showed, what that integration was like in terms of effort, number of people involved, number of months?
Yeah, so I was not involved with that, so I can only comment from the outside. The team has been sort of like fluctuating 10 people. Not everyone is doing that integration part, but so some people can be responsible for integrating like a single thing, but we've been doing this collaboration for like 2 years. So not all of that has been spent on like doing that, but like yeah, a big, like the initial startup was pretty much getting KDL to work. Yeah, a few months probably.
Very nice talk. So it seems like Organa is very robust based on the video you showed. But I'm just wondering how many trials did it take you to shoot that video? Was it just one, or was it just as robust as it was in the video, or?
Yeah, so for that video, we had a 2-hour shooting schedule in that everyone had like something else to do. So we literally shot it once, and then that was sort of the output. And yeah, the only thing I did was I took out, there are some like latencies between connecting to the API. So I removed those just for all of our time. But no, in principle, it is, yeah, it's been pretty consistent in with the startup phase so far.
Okay, great. Any other questions? Not, let's move to the next slide. Thanks,
Awesome,
Martha.
thank you.
Our last speaker is Mehrad from Acceleration Consortium. He's going to talk about large language models in context of natural language processing, I suppose, but no, it was okay. Is it okay? Yeah, just. Great. It's not sure. I want to show something else. Hello and good afternoon, everybody. My name is Merad Ansari. I'm a staff scientist at the Acceleration Consortium, and my research is broadly focused on representation learning, Bayesian optimization, and multimodal foundation models applied to biomaterials and clean energy systems. So at AC, we are focused on developing many self-driving labs. This is a very much interdisciplinary research from inorganic materials to human organ mimicry, where in all these STLs we share this common goal of introducing reproducibility and higher throughput to autonomous experimental workflows. And at STL 0, you're sort of acting as a hub between all these STLs, and essentially we are developing tools that the scientist needs in different labs. So in specific, we are actually interested in optimizing the optimization process of an efficient exploration of the material design space across very different settings. And like on a daily basis, we're actually developing tools that can allow experimentalists who are not necessarily familiar with coding or like AI, use those tools, and those who are familiar actually use them to get much more. So in today's talk, I'll be talking about how we're going to be using large language models to orchestrate our self-driving labs. So there has been a lot of interesting talks today on this concept. So large language models have been widely used for RAG application, retrieval augmenting generation, which means that we can actually extract structured data from unstructured text. But we can do much more beyond that, thanks to taking advantage of the synergy between reasoning and acting. So reasoning means that the large language model can formulate the plan of action. In the context of a self-driving lab, it can, as an example, schedule the experiment, decide what to do next if something goes wrong. And acting means that it can essentially interact with a set of augmented tools that we can provide to the large language model for better decision making. And in this case, we are interested in building domain knowledge into the model. And of course, we want to make the design flexible. So this is why we use an AI agent, which is powered by a large language model. And when I say flexible, I'm visioning this picture where an experimental chemist can enjoy the working from home setting and essentially order the experiment as a text message in Slack, Discord, or whatever API you can consider. So to do that, we give the AI agent a bunch of tools, how to interact with the robotics API in the lab, how to interact with the liquid handlers in the lab, whether it's an OpenTron system or a Hamilton device. And also, we give it access to like safety sensors in the lab. And more importantly, we give it chemistry-informed and physics-informed knowledge. So I will be talking about these three boxes on the right by describing some examples that we've actually worked on so far. So first is where we incorporate chemistry-informed knowledge. Suppose your input prompt is as simple as what are the guidelines for designing water-stable mineral organic frameworks. So we actually worked on this project not long ago with Mohammed, who's in this room, where we developed Eunomia, an AI agent that is essentially tasked to help us leverage existing knowledge from decades of material research articles, scientists, and internet all together. So Eunomia is actually a Greek word. It means stability. That's why I chose it. And how it works is that we give it a bunch of tools. Those tools include having access to online data sets, such as materials project, COD, QMOS, a combination of different research articles coming
from ACS Nature or Digital Discovery, also preprint servers, and more importantly, chemistry-informed knowledge that we incorporate into the model as natural language text. Now, this is important because I will be talking about like water stability property that we actually use Eunomia for to create a data set on. So when it comes to water stability, it's a vague concept among like material scientists. Some say that, okay, I need the MOF to survive a boiling environment for like 7 days. And other scientists is like, okay, I'm gonna be more lenient. I'm gonna call it stable as long as it's water insoluble. So there's like different definitions of water stability. Therefore, you cannot just use like just use simple like keyword search from a research article to like extract this information, and you need like semantic similarity search. So how this works is that simply we ask our AI agent Eunomia to do a role play of an expert chemist, read the papers that are inputted as a PDF or XML, and find all the MOFs. Once you find the MOFs, just find the water stability for them. There are like 3 classes: stable, unstable, and not provided, in case that information is not there. And we would also ask it so that it would present the exact reasoning for the labeling. So with that, we are actually able to do 2 things. One is that we can somehow reduce the black box nature of the model and get a sense why it made the decision it made. And also we can help a lot by reducing the hallucination chance by having the model iteratively evaluate its own reasoning, go through the like answers it provided, and try to like fix bad decisions it made. And with that, we are able to actually curate a very nice structured data set of our own, mapping water stability to the actual chemical structure of the MOF. Note that this is not only for water stability, you can apply it to other properties of interest too. And also, you don't need to apply this to MOF only, you can use other things. And this has been developed as an app on Streamlit, and also it is pretty installable on Python called Tuyol's Eunomia. So I want to talk a little bit about the iterative chain of verification that we use to have the model essentially check its own answers and fix any mistakes it has made. And it actually helps a lot with the hallucination. So suppose you have a human expert chemist on the left, we're going to see a conversation, and we have an AI agent chemist on the right. So just as I described, we would ask it to read the research paper, find the MOFs, and find the label for water stability and justify your reasons. So through the first iteration, the agent reads the research article, finds 2 MOFs here, MOF 1 and MOF 2. So it actually has some justification on water stability for both examples. But for the second step is where it actually evaluates the justification for water stability. So for the first MOF, you can actually see that this information is not about water stability, it's actually about thermal stability, which is why we actually don't want this in our water stability data set. So we throw that away. I mean, not us, but the agent automatically throws that away. And for the second MOF, it is actually talking about water stability, so we keep it. So moving on to the next box here, you're interested in incorporating physics-informed knowledge to the model. And when I say physics-informed, I'm talking about decision makings that come from solving essentially like first principle equations. We don't necessarily need to run a DFT simulation. It can be molecular dynamics, or we can solve the conservation of mass, momentum, energy in a computational fluid dynamics simulation. And if that simulation is actually too expensive to run on the fly, we can use the next best thing, which is the surrogate data-driven model that has been already trained, and we can run the cheap to evaluate the inference model on low commodity resource. And we're gonna look at the quick example shortly. And finally, we can also apply Bayesian optimization here in a sense that in a self-driving lab that you're generating our own limited data, we can actually have this in the loop so that we can do a more efficient exploration of the design space. So I'm a big here, looking at this prompt here, what is the heat capacity of this MOF? So this is the input prompt that we actually give to the agent. We ask for the heat capacity of the MOF at 300 Kelvin. So one idea would be to essentially run a DFT simulation on it, possibly get a hold of this property. But the other idea would be to actually have a machine learning or a deep learning model that can make such prediction for us. And this brings us to this interesting work by Mohammed, who's sitting in this room, where he mapped the heat capacity property with the MOF's crystal structure, even some geometric, chemistry, and atomistic features. So I'm a big advocate on open science. So we're going to actually look at some code here. So essentially, this is powered by GPT-4, and I give the agent a bunch of tools. And here, just for your reference, I'm using LangChain, which is like a great Python module for creating large language model applications. We give it a bunch of tools. Those include how to convert like Smiles string representation to QMOF ID, and how to featureize them off using PyMatGen. And also, this is where we actually call our inference model. It's essentially an ensemble of it's essentially an ensemble of random forest models that have been trained. And with that, for the heat capacity property, we can do regression, and also we can assess the uncertainty of the model. So with that, the only input I give to the model is this. What is the heat capacity of this MOF as a small string at 300 Kelvin? And you can actually see the chain of thought reasoning where the model is actually generating the features for it, and then calls that machine learning model and make predictions of the heat capacity. So this is a tuple that I have as the output. The first one is the average value for heat capacity. The second one is the uncertainty, and you can see that in my output here. So this is very interesting because one of the problems with like large language models is that there's not a great way to assess their uncertainty, and having a physics-based model that can run on the fly as they do the task for you can help you achieve that. So finally, I'll move up to the final example that I have, where we wanna consider safety issues in a self-driving lab and how we can use large language model to essentially handle that. Suppose you have an experiment where you are asked to, like, as a part of the experiment, you're supposed to heat up methanol up to its boiling point. So this is the input prompt that we use to the model. We do not necessarily provide any information on what the boiling what is the boiling point of methanol, or what safety hazard does it come with. And we add an experiment condition here, no would avail. So again, I'll show you some code on this. So like in this case, we provide the large language model with one tool only, and this is a find property tool. Essentially, we are looking up PubChem database for information given a compound name and its property. And here again, you can see the input prompt that we have to the model. We ask it to heat up methanol up to its boiling point, check for the safe hazard, and stop the experiment if it's unsafe. So the agent is like, okay, I do not have information on the exact boiling point of methanol, but I can look it up given this tool that I have. It finds this information. Same thing happens with the health hazard, and finally, it's saying that, okay, since the fume hood is not working currently, maybe this is not the best experiment to do. Of course, this is our way of automating things. You could think of like many ways to do this. You can, of course, hard code everything. It's going to be like a very tedious process. You don't want to do that. You could be also uploading all the material safety data sheets that show up in your experiment to your model. Again, another tedious process you don't want to do. So this is one way to handle. So finally, I want to talk about this tool that I recently developed at AC. So essentially, it's called Heisenberg, and you can think of it as a chemistry-informed version of ChatGPT working within Slack API. Currently, it has access to like a lot of online tools. Thanks to SERP API, it can do like a live Google or Bing search. It has access to Pumpkin. It can do RAG from documents. I've been working. I haven't implemented it yet, but it's soon going to have access to papers on preprint server as well. And you can text message it, or you can actually voice message it. So just a quick showcase here. This is some of the chats that I have it. You can ask different kind of questions like Pythonic code, or you can even ask about like synthesis steps of different materials. Of course, this I wouldn't 100% trust this, but it is like work in progress. So the results I showed you were all thanks to these amazing people that you can see in these two pictures here on the right. You can see people from the AI for Chemist lab, where Mohammed Musavi is the PI. And on the left, you can see my friends and colleagues at the Acceleration Consortium. With that, I conclude my talk and happy to answer to any questions. Thank you.
Excellent. Any question?
Yeah, going back to the materials, if we prompted to pick up on mobs that are not like water stable, let's say, find ones that are that have high thermal stability, do it still work with low accuracy, or is it just doesn't work?
You can try it for any property of interest you want. So it doesn't have to be water stability. It can be thermal stability. It doesn't even have to be moth. You can try it with peptides or other things.
Other questions?
For the tools like you're using the publication with them, discuss like for ACS and obviously we have some non-sensitive issues, so directly we can access the publication through some API. Or like we have to manually download them.
Short answer, you can't. Long answer, so if it's coming from ACS, technically you can't. Like the work that we did with Eunomia, we had like an agreement between University of Toronto and ACS. That's how it worked. They provided us with all the XML files, not even PDF, all the XML files from those research articles. That's the tricky part with ACS, but with preprint servers like Archive or like ChemArchive, they have API, you can actually download it from them.
That also kind of like to refer, like there's so much vast knowledge out there. There's a lot of them are good because when we look through publications, we look for good impacts journals and stuff like that, right? How do you sort of sift through those that are kind of wonky, like the science are not quite right? You don't want them to pollute your model, right? So how do you get around that? Or how do you ensure that
We have a clean model.
That's a great question. So one thing you can do is that you can add like internet search to your tool, to your model as a tool. And of course, we know there's a lot of crap on the internet, so you don't want to trust. You don't want to trust that. But when it comes to like papers, you can. It depends on your use case. You can have like a predefined set of papers where you can do RAG from. Obviously, if you just use like Archive API to do a search based on like certain keywords, you're gonna run into papers that might be really good, might be really bad. They are not peer reviewed. So it's essentially up to your own decision. Yeah.
Great. Question?
So the prediction example that you gave, was it just one tool that it had access to, or were there multiple? I guess, how many tools were at play with the property prediction?
For the MOF one, so that I think there were like 3 tools. It's essentially like a series of actions that needs to be completed. So like the main input from like the user is the small string representation of the MOF, but our model actually takes in I think I wrote the code some time ago, but we actually have to map that small string to the QMOF ID. From the QMOF ID, we get the chemical structure, and from the chemical structure, we can actually generate all these descriptors that that were used in the model. So, like I think like 3 to 4 tools, but you can, I guess, combine the tools all together. You maybe have like a bigger wrapper around like one tool to do the task for you.
Does anyone need Anthropic credits today for tomorrow? Ben's asking. So I'm guessing we've got sponsorship from Anthropic.
I would take it.
Okay, great. If no more questions, let's thank Merad again. Thank you. And it was a good series of talks. Thanks again to all the speakers. Now we can get back to coding.
Back to work.
Back to work, yes.